So let me briefly introduce the chairperson of today's session, Dr. Sunil Basarkar. He is working as General Manager at Afcons Infrastructure Limited, Mumbai, and he heads Geotechnical Group supporting land, marine, and infrastructural EPC projects. He is a graduate in civil engineering from I.I.T. Roorkee and postgraduate in geotechnical engineering from Pune University, and earned his PhD in pile foundations from IIT Bombay. He has field experience of over 17 years with the infrastructural organizations, in addition to full-time teaching and academic experience of about 16 years. And he published several papers in international journals and conferences. He is a fellow of the Institution of Engineers India, Indian Geotechnical Society, National Executive Committee member, and Deep Foundations Institute, DFI India, and also editorial board member, DFI Journal USA. Welcome you, sir.
Thank you.
Co-chair of this session, Dr. P.L. Meyyappan. He completed his BE from Bharatiya University and postgraduate from Karunya University, and obtained his PhD from Kalasalingam Academy of Research and Education, where he serves as a faculty member now. And he has published around 30 papers in journals and conferences. And he has received several awards and initiated several collaborative works with the Coastal Management Program with the Kuwait Institute for Scientific Research. Welcome you, sir. Now,
good evening, sir.
I will hand over the session to the chairperson and co-chair, please. Please take over.
Thank you very much, Dr. Srival sir. And let me convey my appreciations, my pride, my privilege to be chairing this important session in the realms of the liquefaction, which is a very burning issue as far as the infrastructure projects are concerned. You can call me a half infrastructural man and half academician, spanning to the tune of about 32 years. So thank you very much to the organizers of this international conference for the opportunity to chair the session. It's my pride and privilege to introduce the keynote speaker for this session, Professor Ronald Andrus. Professor Ronald Andrus did his BS in geology and mathematics in year 1983 from Brigham Young University. Did his MS in civil engineering during 1986 from the same university. He completed his PhD during 1994 from the University of Texas at Austin. He has expertise in geotechnical engineering, soil dynamics, soil characterization, non-destructive techniques, earthquake engineering, earthquake hazard mapping, and liquefaction. He is a professional engineer in South Carolina. He has a professional society membership of I.I.Sc, Geo Institute, International Society of Soil Mechanics and Geotechnical Engineering, Earthquake Engineering Research Institute, and American Standard Society of Engineering. So thank you very much, Professor Ronald Andrus, for gracing and for acceding to the request for being in fact, the keynote speaker for this session. Without wasting much of the time, I'll pass on this august platform to Professor Ronald Andrus.
Good evening, good afternoon, good morning, wherever you're at in the world. I very much appreciate the introduction. I'm speaking from South Carolina in the United States. It is my pleasure to be part of this conference. I compliment the organizing committee of this conference who have organized and reorganized this conference during this COVID-19 pandemic. I'd like to also begin by acknowledging my co-author, Barnabas Benwali, who has contributed greatly to this presentation, as well as many other graduate students that have worked over the past 20 or so years in developing the material I will be presenting. My presentation outline is as follows. First, I will review general liquefaction susceptibility criteria of aged soils. Then I will discuss the aging or diagenesis in sand deposits. Then we will look at cases of Holocene liquefaction in Pleistocene deposits, followed by several proposed methods for estimating the aging or diagenesis effect on the cyclic resistance ratio or CRR based on lab test, lab and field test and ground behavior observation, then conclude with a summary. So in 1978, Yount and Perkins published a paper on liquefaction susceptibility that has been used for developing susceptibility maps. In their publication, they talked about the susceptibility of soils based on age. And shown here is a graphical form of what they presented, where recent deposits, those deposits less than 500 years, had a susceptibility of very high to high qualitative values. And then for Pleistocene and older, they had a susceptibility of low to very low. We would like to move beyond this qualitative description of soils and come up with quantitative methods for estimating the effect. But first, I'd like to talk about the aging or diagenesis of sands and just focus on the initial stage, because that is what we generally will encounter when we're talking about the liquefaction of Pleistocene or older deposits. The figure that I'm showing here, I've adapted from Borkum, who studied the diagenesis of a Cretaceous sandstone. And this is just the initial stage where we have our sedimentation, the deposit being formed, the grain-to-grain contacts are initiated. And then as we go in this initial stage, we are getting creep occurring at the point contacts of the grains. The pressures are high, and we will start to get pressure solution at those contacts, followed by precipitation of cement near those contacts. So in this figure, the blackened area near the point contacts is where we're getting cementation. And then as it progresses at those contacts, some of them turn into concave, convex, convex contacts. Factors that are influencing the initial rate or the rate of initial diagenesis include pressure, temperature, and mineral content. Now, what we gain in terms of strength from creep and cementation, this can be undone by certain events, one being liquefaction. The photograph on the left shows a sand blow or a large sand boil that occurred in a 200,000-year-old beach deposit during the 1886 Charleston, South Carolina earthquake. Other events that can undo creep and cementation are some construction activities. In the photograph on the right, it's illustrating the installation of a buried pipe that is greatly reworking the soils, and even below the excavated part, the vibrations are weakening the contacts. Much of our work has focused on the Charleston, South Carolina area, and we see in this slide a geologic map of the greater Charleston area, which shows beach ridges ranging in age from less than 10,000 years to when we go 40 kilometers inland, they're over 700,000 years old. Now, during the 1986 Charleston earthquake, there were large sand boils or craterlets or blows, whatever you want to call them, that occurred at many locations within the Pleistocene deposits. Also, what was mapped are areas where we had horizontal ground displacement. The trace here is the trace of the surface rupture of the fault, and it's actually mostly inferred because it's not well defined. The sediments here in Charleston are 800 meters thick before you get to the basement rock. And so by the time it gets to the surface, it's not that well defined. But you can see that most of the, and I'm looking for that cursor again. Yeah, most of the ground failures are occurring near the fault. In the next slide, it's going to present a histogram of the number of ground failures in each of the geologic units. This histogram was created by Tihara Hildari, a graduate student here as part of her dissertation created this. We see that the largest number of cases are occurring in the 200,000-year-old QTS deposit. And as we move away from the fault, the number is decreasing generally, but still larger in the younger deposits and less in the older deposit. So definitely proximity to the source zone is a factor in liquefying these older deposits. South Carolina is not the only place where we have Holocene liquefaction in Pleistocene deposits. We have, so here on the map, we're in South Carolina, but in Arkansas, Tennessee, Idaho, there have been cases of Holocene liquefaction in Pleistocene deposits down in South America and over up in Europe, the Middle East, and in China. All have reported cases of Holocene liquefaction in Pleistocene deposits. When we plot the frequency of those cases, we get more in the younger Pleistocene deposits and less in the older, supporting the conclusions of Youde and Perkins. And then when we divide it into deposit type, alluvial, fluvial, beach, and lacustrine, also agreeing with what Youde and Perkins published in 1978. In terms of quantifying the effects of diagenesis, what we're talking about, what we're talking about is we have the CRR from the commonly used charts that have been proposed and are used in practice. But these charts are based on young soil deposits. And so in order to apply them to older soil deposits and to get a correct prediction, we need to add or apply a diagenesis correction factor. And we have denoted it, it's denoted in this presentation as KDR. There are a number of ways that we can come up with this diagenesis correction. One way is to base it solely on lab test, where we define KDR as the CRR of the intact specimen, the undisturbed specimen, divided by the CRR determined from laboratory testing on freshly reconstituted material from the intact. And shown in the figure here are three relationships based on lab test. The earliest being from Seed, 1979, who studied 4 or 5 different sands and came up with the relationship shown in blue. Arango, Lewis, and Kramer extended what Seed did by looking at two older deposits, and their relationship is shown there in green. And then Hossein Hayati, as part of his dissertation work, compiled the data that are shown in red circles and created the regression line in red. Later, Barnabas Benwally, as part of his dissertation, added a couple data points from Christ Church. And you see that they're all agreeing, in fact, within the scatter of the data. An important note is the value of time when KDR is 1, when we have essentially no aging or diagenesis effect. And in this case here, it occurs about 2 days, which is very reasonable given that reconstituted specimens tested in the laboratory are usually just 1 to a few days old. Unfortunately, those relationships do not work for all soils. Troncoso reported results of tests on mines tailings, and those results, which were plotted here in brown, indicate a faster rate of strength gain than that of predominantly quartz sands. Another category of diagenesis correction factors are those derived from lab and field tests. That is, laboratory tests to determine the CRR of the intact specimens, divided by the CRR determined from existing curves or new curves to get that correction. And I'm just going to focus on the work of Hossein Hayati, given the time that I have. So presented here are two plots. One is based on the one on the left is based on SPT blow count. The one on the right is based on cone tip resistance. The yellow circles are laboratory determined CRR values that are plotted versus the corresponding field SPT blow count. The curves that are shown are 50% probability curves that were derived by from various researchers. You can see that there are scatter in the prediction of the 50% probability curve, and we are using the middle range of that, the red curve, as the reference CRR. We're using 50% probability curves because experimental data is scattered about a mean. And so we want to try to approximate the mean as best we can. In the next slide, what it will be shown are the values of CRR of the yellow dots divided by the values of CRR of the red curves, plotted versus time. And this is a plot that was created by Hossein Hayati. The red points are the points that you saw in the previous slide. And we have the regression line shown. There are some extra points that were added by Barnabas Benwally, which agrees very well with the points compiled by Hossein Hayati. An important thing to note is the slope of this line, 0.13, is very similar to the slope of the line based solely on lab tests, that being 0.12. Another important point of this slide is the value of time when KDR is 1, and the value of that and the time that corresponds to KDR of 1 is 23 years, which represents our calibration of age for commonly used CRR curves. And that makes much sense because those CRR curves are biased to young deposits and measurements made 1 to 30 or more years after the earthquake. So coming up with an average age of 23 years for those curves is very reasonable. The third category of diagenesis correction factors are based on field test and ground behavior observation. There are various approaches within this category. One is to use the liquefaction potential index, another minimum and maximum factor of safety, and a third is to develop new CRR curves. I'm going to highlight each of those three approaches in the following slides. So this slide highlights the derivation of a diagenesis correction factor using the liquefaction potential index applied to CPT results from the Charleston Peninsula. And when we talk about the liquefaction potential index, this was a parameter that was proposed by I.I.Sc and others that is defined as an integral of 0 to 20 meters on a function that relates to the factor of safety of each of the layers in the top 20 meters. And it only considers those layers that have factor of safety less than 1. And in this example, I'm looking for my cursor again. The open red square would be the prediction for the 100,000-year-old Wando Formation. We would have a LPI of 17 if we applied no correction, and the prediction would be severe liquefaction. However, little to no liquefaction occurred in the Wando Formation on the Charleston Peninsula during the 1886 Charleston earthquake. In order for it to agree with field behavior, we need to apply a deposit correction factor of 1.8 to pull it down to 5, which would be the threshold of getting of predicted ground failures. So we need to apply a correction or we incorrectly predict behavior. Here's another example of applying the liquefaction potential index. This example was done by Barnabas Benwally, and it's looking at the less colluvium deposits at the base of the Port Hills. And I'm just looking to see if I can, okay, I got, it's these deposits at the base. No sand boils, silt boils were identified in those deposits, indicating that liquefaction was not a factor in their behavior. And without a correction, a diagenesis correction, severe surface manifestations of liquefaction are predicted. And this would be for the February 2011 earthquake. When we plot the value of the diagenesis correction for the Port Hills, it plots here. The age range would be in this range right here, but it's well above the data that Hossein Hayati and Barnabas Benwally compiled for predominantly quartz or silica-based sands. So here's another example of where time is not doing a very good job of being the predictor of the effects of diagenesis. Here is a slide summarizing the approach of Tohata and others, where they used minimum and maximum factor of safety. What they did was at the liquefaction sites, they determined what the minimum value of the factor of safety was, and at no liquefaction sites, the maximum. They plotted it on this figure, and it shows that kind of the threshold for surface manifestations of liquefaction, the factor of safety is decreasing, indicating a strength gain with age. Shown here is the proposed value of Tejada and others for the diagenesis correction, 1.4 for soils older than 400 years, which agrees with the data of Hossein Hayati and Barnabas Benwali. Shown here is a new CRR curve that was proposed by Dobry and others, where they looked at data from the Imperial Valley, California, and they noted that the line separating cases of liquefaction and no liquefaction in the natural sand deposits plotted significantly above the line for uncompacted fills. As we have noted before, time is not necessarily always the best predictor of the effects of diagenesis. A promising alternative, more robust parameter is the measured to estimated shear wave velocity ratio. And this is a very simple concept. We're going to take the measured shear wave velocity, adjust it for overburden effects to a reference overburden pressure, and then we're going to divide it by an estimated shear wave velocity. Here are the estimated equations that we have been using right here. This is corrected cone tip resistance, corrected SPT blow count. And these equations are being derived from data obtained in the younger Holocene sand deposits that are plotting. The purple curve here is the plot of the first relationship based on cone tip resistance. The data around it is the data that the regression is being based on. Many of these young soil deposits liquefied in previous earthquakes, but that's our reference there. And now we've come to other sites and found that in older sites that haven't liquefied, we get much higher values. And so what we're going to do in the next slide, we're going to show this same data, but we're going to take the shear wave velocity and the measured values and divide them by our reference curve here to come up with a plot of MEVR, measured to estimated velocity ratio, versus time. And we have time here. We've been very careful on how we've defined time. It's time since initial deposition or critical disturbance, that is liquefaction, and our measured to estimated velocity ratio here. We can see that there's a strong trend in the data, that it's increasing, that MEVR increases with time. We can also see that there's significant scatter in the data, which is likely due to varying degrees of diagenesis within the same deposit. Shown here is the created by Hossein Hayati, where instead of time now we're using MEVR as our predictor variable for our diagenesis correction. And we get this relationship here. The R squared here is 0.7 versus the 0.72 here versus the 0.6 something with time. And when we look at the Port Hills case history and extrapolate the Hossein Hayati equation, it agrees very well. In fact, much better than when we are using time as the predictor variable. There have been other proposed predictor variables for the diagenesis effect. The small strain modulus Gmax by cone tip resistance, that same ratio multiplied by a normalized cone tip resistance, and then that value of kg divided by some estimate or reference kg. They have been proposed. Now we can compare these three additional predictors with the MEVR predictor, because shear modulus is directly related to shear wave velocity. each of these ratios can be rearranged into a ratio of measured velocity divided by the normalizing function of QC. And that is what is being shown here in this plot. So this right here is our estimated MEVR relationship. This is the reference relationship that's being assumed. And I've lost my cursor again. The G max over QC, we got the KG relationship and the MEKG. And we can see that the shapes of those 3 or 4 estimating or reference shear wave velocity relationships are different. And because they're different, we should expect their ability to predict the effects of diagenesis to be different if they have different shapes. Shown here is a comparison of the 4 predictor variables, how they're predicting the diagenesis correction factor. This figure was created by Barnabas Benwally. We have on the upper left the relationship in terms of MEVR. And the important value here in these slides to focus on is the R squared and the root mean squared that's given in the lower right-hand side of each figure. So for the MEVR, the R squared is 0.62. For Gmax over QC, 0.43, KG, 0.14, and MEKG, 0.14. So MEVR is better in terms of R squared, and root mean squared error, 0.27 for MEVR. Gmax over QC 0.33, KG of 0.4. So the lowest root mean squared is MEVR. So in both indicators, MEVR is doing the best job of the 4 in being the predictor variable for the diagenesis effect. Plotted here are 2 relationships between MEVR and the diagenesis correction factor. And this is being based on field tests. So we have the relationship shown in red by Hossein Hayati. And then Barnabas Benwally, he reviewed the data compiled by Hossein Hayati. And if the data didn't contain a certain set of information, he omitted those data, but he added new data. But in that process of interchanging data, the regression did not change much. And his regression line is shown there in purple. Pretty much the bottom line is that the diagenesis correction factor is approximately equal to the MEVR. So when we're calculating MEVR, we're actually approximating that correction factor. In summary, initial aging or diagenesis includes creep, pressure solution, and precipitation of cement. Liquefaction and some construction activities can erase the strength gain from creep and cementation. Sites of Holocene liquefaction and Pleistocene deposits support the need for assessment in older deposits. 7 proposed relationships exhibit similar rates of strength gain per log cycle of time for silica-based sands. However, tailings and lush colluvium deposits can exhibit significantly greater rates of strength increase. MEVR, or the measured to estimated velocity ratio, is a better predictor of diagenesis effect than time, and MEVR provided the highest R squared and lowest root mean squared of 4 predictor variables. To end, I'd like to again thank you for your attention. Although I could not see you, I very much appreciate you listening. I appreciate the funding that I have received over the years and the many graduate students and others that have provided support that have made this presentation possible. Thank you.
Thank you very much. In fact, I could see introduction of diagenesis correction factor in the computation of the CRR values. And it is very apparent that if you don't apply the corrections, the severity of the liquefaction is in fact amplified, if I'm correct. And this is a new concept, and that takes into account the historical and geological account of determination of these correction factors, KDR. Three modes of determination had been conveyed by Professor Andrews, and definitely we would like to see more and more contribution coming out from these studies, as I find that this happens to be the gray area and a sunrise in realms of the research. I find that much of your assessment and analysis and research are based on the sands produced from various formations, geological formations, whether they'll be applicable for the very fine sands, silts, soft clays. This is my first question to you before I pass on the question session to the presenters, the presentations and the audience. So the question is, how far the information on these correction factors are there for the soft silts and clays?
Well, that's a wonderful question, and one that deserves new research or research on. The deposits that I've presented, I think very few of them involved silty soil. So I'm going to leave it at that. Let's see the research, and I think that the application will work, but there may need to be some refining of our ability to predict silty soils based with both with the CPT as well as with other measurements. So yeah, we'll just have to see. I'm not going to say that predict that it's going to be perfect, but it's certainly an exciting question to pursue.
Would you be in position to present a chart, easy chart? A normal trend in the practice is to go in for a spreadsheet, which normally uses the IDRIS method, the original method of computing the liquefaction potential, that is CRR by CSR. So in your contribution, you have introduced this correction factor. So that means the sheet can be extended with this factor, the KDR factor, and there will be a realistic determination of the liquefaction potential. So that will be the great, it is already, we can see the contributions are there, but it definitely adds to the accuracy of the prediction of the liquefaction. Our infrastructural industry, they have extended the potential effect on the fine sands, fine silts, and the soft clays also. And belonging to the Mumbai region and the coastal areas, marine clays, had been playing a dominant role, and we are plenty often asked to assess the liquefaction potential of the soft soil. So this is from my side. I can see one question in a question answer box. The question is, can we apply the IDRIS chart and CSR/CRR approach to evaluate the liquefaction potential for all types of soil, irrespective of geological deposits at different times?
So what the data are showing that I presented today is that the charts that are commonly used, such as the Idriss-Boulanger charts, they are based on young soil deposits and measurements that are made soon after the earthquake. Just, sometimes they get to the site in less than a year. Other times it's a few years. Other times they return after, tens of years. But still, those relationships are biased towards these young deposits. Yes, there's differences, differences between the CRR curves, but the general corrections that we presented, they may not be, perfect for all, but they're there in the ballpark. of what needs to be done in order to correct the CRR. When I didn't mention this during my presentation, but I had a student named Danny Ballin, who was one of the first to apply the LPI procedure to the Charleston area. And when he did it, he predicted that 98% of the area should have experienced severe liquefaction. And I go, well, let's look at the observed cases, and 98% of the area did not experience severe liquefaction. In fact, there were some areas where there was not, and we were predicting severe liquefaction. And so if you do not pay attention to the effects of diagenesis, you're going to over-predict or under-predict their strength and get predictions that do not agree with field behavior. So we need to be paying attention to this effect in order to better refine our predictive equations, as well as to help us better understand how we proceed with our engineering designs.
Thank you very much, Professor. In fact, India has seen the earthquakes, and the geological information is definitely indicative of the high likelihood of the earthquake. We have, as you are aware, several zones of seismicity within India. One on the western side, we had observed what we call as a Bhuj earthquake, and that has defined the whole seismicity map of India. Now, a very recent earthquake we have seen in the month of April this year, although being of a low Richter scale of just 6, the liquefaction was very, very evident, and it was even captured by the local villagers and people. So very common in the maps of India. I thank you very much. Any queries? Last query from our panelist.
Yeah.
I will pass it on. Yes, Professor Pathasar.
Yeah, thank you. Thank you, Mr. Chairman. Thank you, Professor Andres, for a very nice presentation. So I have just a couple of questions. What is the simplest way of finding the age of a soil? First one. And second question is, see, when those older soils are disturbed during the construction activities, so what's the minimum timeline to realize the effect of aging, perhaps maybe for the gain in strength? For example, the pile installation in those soils, after a certain period of time, the effect of aging would also increase the capacity of the piles. So what would be the minimum timeline? And last question, maybe you can address that, is the carbonate content. Now, whatever the results we saw is on the siliceous quartz. So what will be the effect of aging on the carbonate soils? Thank you, Professor.
So you've asked some very important questions. In terms of determining age of the deposit, that can be a very difficult thing, particularly if you're in an area that's new to you. And that is one reason why we went to the measured to estimated shear wave velocity. So we are not trying to estimate the age and where liquefaction occurred in the past and where it differed. We're basing the measured to estimated shear wave velocity ratio is a parameter that we don't have to go through that process of trying to decide age. It also does a better prediction than when we do come up with age. So I'm strongly encouraging use of the measured to estimated shear wave velocity ratio. In terms of kind of the minimum time period, there's an interesting study that was recently published by Professor Woods out of the University of Arkansas that was published in the Journal of Geotechnical and Geoenvironmental Engineering recently, where they went back and looked at to try to see the aging effects at sites in Christchurch, New Zealand, and between earthquakes. So we're talking about, less than a year to a few years. And they did see an influence of age. So we're picking this, it's there, and it's occurring, even after the deposit starts, even just a few years afterwards. That effect is being seen and was, reported by Professor Woods and his colleagues. In terms of the calcium cementation, so we have different types of cement. And if there's grains that have a lot of, that are carbonate based, we're going to get probably a faster rate of increase. So that would be another reason why to avoid use of age and try to move to a predictor variable such as the measured to estimated velocity ratio, because the different mineralogies are going to produce different rates of strength gain.
Thank you. Thank you, Professor. Thank you.
Thank you, Professor Ronald. Thank you very much for enlightening the presentation. And it is really a new development in this area of liquefaction. Without wasting much of my time and the panel's time, I will pass on the remaining part of the session to my co-chairman, Professor P.L. Mayappa. Over to you, sir.
Thank you, sir. Thank you, Professor Andrews, for your wonderful session.